Dear students, this is tutorial number 3. It's about distributions. I have made some changes in the lecture to make it easier for you. So please download the lecture from Moodle again. Okay, we are going to discuss two important distributions in this lecture. The first one is Bernoulli distribution and the second one is geometric distribution. You are all familiar with Bernoulli distribution. You have taken it from probability and statistics class, I guess. Okay. Bernoulli distribution is like, it can be described as a tossing a coin example. Define x1 if the heads comes up, or define x0 if tails comes up. It's basically a binary distribution, either 1 or 0. Both realizations are equally likely. For example, if you toss the coin and it appears a head, it has 50% chance, and if the tail has also 50% chance. So both the probabilities or both the outcomes are equally likely or equally in their probabilities. Examples of such distribution that are not usually equally, for example, success of a medical treatment. Sometimes this is not like equally or not, it's just like 50% or 50%. Depending on the medical treatment, sometimes it's like 90% or 99% the success, the medical treatment will be successful, for example. But there are two outcomes. One is the medical treatment is success, the other outcome is not success. Okay. Another example, interviewed person is a female. For example, if you have there are some applicants for a job, and the applicant perhaps be female or male. They are not equally chance, for example, depending on the job type or job description. Students may pass the exam. The rates of students passes exams are differently from one subject to another subject. Transmittance of a disease, it's also can be considered as a Bernoulli distribution, either such that like the disease can be transmitted or the disease cannot be transmitted. Okay. Usually, Bernoulli distributions accompanied with the parameter phi or theta, sorry. For example, x takes two values, either 0 or 1. The probabilities of being 0 is p, then the probability of being x equal to 1 is y minus p. If you have p, then you will definitely have 1 minus p. They call it as like reverse probability or inverse probability. So if you have two outcomes such as 0 and 1, if the probability of the outcome is 1 is 0.6, then the probability of the outcome is 0 is 0.4. The total of probabilities has to be equal to 1. The frequency function of this x is the probability of x depends on theta to the power of x multiplied by 1 minus theta to the power of minus 1 minus x for x such that is 0 or 1. Otherwise it's 0. This is not a tough question. If you think about it, like if you substitute x as 0, what will you all get? Theta to the power of 0, the outcome of this portion of the equation will be 1, because everything is power to the 0 is 1. Then the final outcome will become 1 minus theta, which is 1 minus 0, 1. So the probability of x will be for 1 minus theta only. If x equal 1, then this outcome will be 0, so this one will be 1, and the only left we have left only with theta to the power x. This equation describes the Bernoulli distribution as shown in this graph as well. Okay. Often x will equal 1 if the event A has occurred, otherwise it's 0 if the event is not occurred. Okay. Example of such a distribution is when A is the blood pressure is 140/90 millimeter Hg. Hg is like for mercury. Usually they use the mercury. Before they used this instrument, mercury instrument, to measure blood pressure. So they usually measure the height of the pressure of the mercury by using millimeters. Okay. If A is like above these numbers, then the x will be 1. Otherwise, it will be 0. Okay. Let's take a simple example of Bernoulli distribution. Suppose that we have x1, x2, x3 to xn. Be independent Bernoulli number random variables with same parameter theta. That means that they all have the same probability. Frequency function of x1 to xn is probability of x1, x2, x3, xn, etc. will equal to probability of x1 multiplied by probability of x2 multiplied by probability of x3, and etc. The same here. The same equation can be applied, probability of Bernoulli distribution here, but in multiple times. How? Like probability of x1 plus theta to the power of x1 plus x2 plus x3 plus xn, etc. They are all multiplied by 1 minus theta to the power of n minus x1, a number of independent variables, minus x2 minus x3 minus xn, etc. For each xi, they are either 0 or 1, and I belongs to the set of n independent Bernoulli random variables. Example for paired sample sign test. Okay. Study success of a new elaborate safety program. Record average weekly losses in hours of labor due to the accidents before and after installation of the program in 10 industrial planets. We have 10 industrial planets. We are going to record we have a record of average weekly losses in hours of labor due to the accidents. Suppose that there is an accident in one planet, the whole work will be stopped, and there are some hours will be lost. So the company or the main head of these industrial planets has installed a new safety program to see what will happen, what will happen in the industrial hours, what will be losses in these, what change will be changed in the losses in these labor hours. Okay, these are the 10 planets. Before installation, they encountered 45 accidents, or 45 loss of hours. And the second planet 73, and the third, and etc. To the 10th planet, they have 17 lost hours. After installing the safety program or informing the workers about the safety program, the number of lost hours has been reduced fairly. For example, for the first planet, it becomes 36 hours lost, for the second planet, for the third planet, and so on. See that like in planet number 5, it actually become worse because of the safety program. The number of planet accidents increased. So to define the Bernoulli distribution for this number of independent Bernoulli random variables with the same parameter theta. Why the same parameter theta? Because they are all identical planets, and the probability of losing hours are the same in all planets, but based on the time, based on the action of them, they may differ from one to another. The results of such planet safety program, we have two choices here. If the value is greater than the second one, then it will be 1, otherwise it will be 0. Okay, the before value is greater for the planet 1, for the planet 2, for the planet 3, and all the planets except for planet number 5. The number of losses become more, so we mark it 0. So the xi's are independently Bernoulli distributed with unknown parameter theta. Now let's jump to all you need to understand it here is to follow this rule all the time, and for multiple independent variables with the same parameter, you will follow this rule as well. And this the probability, we don't have the probability here, we have numbers. If we have the probability for each one, then we will follow this rule. It's the same as this rule but with multiple integers. Okay, let's jump to geometric distribution. Consider a sequence of independent Bernoulli trials. On each trial, a success occurs with a probability of theta. It means that for each trial, the probability will be changed. Let x will be the number of trials up to the first success. Okay, what is the distribution of x? The probability of number of success in x minus 1 trial is 1 minus theta to the power of x minus 1. And the second option, the second term, is the probability of one success in the x trial is theta. Okay, the answer for this distribution should be either like this or this. So the frequency function of x will be probability of x, the same as the Bernoulli equation, theta minus multiplied by 1 minus theta to the power x minus 1. But we are missing one thing. We don't have the theta to the power, if you remember, to the power x here. We have to 1 because we have one success trial all the time. Okay, we will say that x is geometrically distributed with the parameter theta. Simple example of such a geometric distribution is, suppose that a batter, if there is a baseball game, usually a batter tries to hit the pitcher ball. Suppose this batter has a probability of 1 divided by 3 or third to hit the ball. What is the chance that he misses the ball less than 3 times? Usually in these types of question, you should read the question many times to understand what outcome or what's exact number we need from you. Okay, what is the chance that the batter misses the ball less than 3 times? It means that he will miss the ball in the first trial, he will miss the ball in the second trial, he will miss the ball in the third trial, and that's it. So the number x of balls up to the first success is geometrically distributed with the parameter 1 of 1/3. Thus, for the probability of the batter misses the ball less than 3 times is less than or equal to 3 times. Remember that this number 3 times means that the number 3 is included to the probability. Is for the first time, for the first Bernoulli distribution is 1/3. For the second time is 1/3 multiplied by 2 by 3. For the third time is 1/3 multiplied 1/3 2 3 square. The total probability is 0.7037. You will ask me why these numbers come. Where does these numbers come up actually? First, Bernoulli distribution. We don't have many parameters. We have only one parameter, which is theta. what is the value of theta here is 1/3. So theta is 1/3. This number is fixed for all trials, for all 3 times. So you will see that 1/3 appeared in the first one, but the second one does not appear. Why? Because for the trial, for the first time, x is equal 1, 1 minus 1, the second term will equal to 1. So we don't have the second term here. This disappeared because it's 1. Everything multiplied by 1 is the same. Okay. For the second time, the number x will be 2. So 1 minus theta will be 2/3. Be 2 by 3. Okay, that's cool. Okay, for the third time, x will be 3. So x will be 3. 3 minus 1 is what? Is 2. So we have 2 from the first one, because 1 minus third is 2 by 3. Squared, the square comes from x 3 minus 1, which is 2. So you have to calculate this using a calculator, and you will get the geometrical distribution of such problems. Okay, why these distributions are important to understand? Because we don't have Bernoulli trial all the time. For example, if you say that you have a game and you are trying to throw a ball to a basket, for the first time you say that you are very good in throwing balls to the basket. You have 90% chance to put the ball in the basket in the first time. In the second time, you also have the same probability of 90%. For the third time, it is 90%. So what is the total, or when you are going to definitely, or what is the probability that you will at least put the ball in the first 3 times? You will use geometric distribution to calculate the probability. Thank you for listening. If you have any questions or extra clarification, you can ask me on Moodle, and I will definitely make another video for you to understand very well. Thank you.